Okay, so in this example, we are interested in explaining the standardized outcome on a final exam shown by this variable in terms of percentage of classes attended, prior college GPA, ACT score, and then we have included an interaction term between prior GPA and attendance to show that the effect of attendance on school performance depends on prior GPA. And the idea is that the class attendance might have a different impact for students who have performed differently in the past. So prior GPA, it is probably a very good indicator of what will be the impact of attendance rate on student performance. We can say that the students who have performed better in the past, shown by their prior GPA, if they attend more classes, their GPA will go up. And the students who have not performed better previously, even if they attend 100% of the classes, their final outcome may be different. So this means we want to measure what will be the impact of the change in the attendance rate on the final outcome. We can see that it depends on prior GPA. So essentially the impact of one variable, it is a function of another variable. We can calculate average partial effects based on the average GPA in the sample. Let me show you this example in R. Okay, so here we are. The data set is attend. I have attached the data set, and here this is my final outcome variable, and this is my interaction term between attendance rate and prior GPA. I have inserted a star in between these to estimate a model like this model where R will include not only attendance rate and prior GPA as separate variables, but also will include an interaction term between these two variables in the model. And then I have ACT in the model, and then the square of ACT. You cannot insert ACT square in this highlighted form in this regression equation because it's a column vector, and you cannot take the square of this column vector as this says. You have to multiply it with this what we call identity matrix to get the square of ACT. We are doing the same thing with prior GPA. We are taking the square of it by multiplying it with the identity matrix. And I have already saved the results of this as model 1. We can look at the summaries. So these are our two coefficient values. Our coefficient value of attendance rate is minus 0.0067, and the coefficient value for the interaction term between attendance rate and prior GPA is 0.0056. And we want to measure this impact on the average value of prior GPA. And the prior GPA in the sample is about 2.59, so we can multiply this and we can get the average partial effect as 0.78. The average impact of the change in the attendance rate on student performance based on the average prior GPA is 0.78, and we will get this impact by using this equation. But the problem is, if we remember from our previous discussions about measuring the impacts of two or more variables, we do not have standard errors for these impacts. We can get the direction and the magnitude of the impact, but we do not get whether this impact is statistically significant or not. We don't know about this. For that, we need to calculate the standard errors, and as I said in one of my previous videos, it's not very easy to calculate the standard errors because we have to calculate the covariance between these two variables. Okay, so we can also calculate average partial effects by regressing this model. So I'm going to regress this model, and then I'm going to extract all these coefficient values and save them as betas. So this function coef, it will extract all these coefficient values, and next I'm going to use the formula that I showed you earlier, that is beta from attendance plus 2.59 times the beta of the interaction term, and in this way we'll be able to calculate beta 1 plus 2.59 times beta 6. As we can see, this is the exact value that we calculated manually. It is 0.0078. We can check the statistical significance of this interaction term by using this library car and then testing this hypothesis that whether beta 1 plus 2.59 times beta 6 is equal to 0 or not. So I'm going to save this hypothesis, and then I'm going to pass this hypothesis to linear hypothesis function. This is my model and this is my hypothesis. Okay, so this is our hypothesis that beta 1 plus 2.59 beta 6, which is the interaction between attendance rate and prior GPA, is equal to 0. And we see that the p-value is 0.003. It's very low, which means we reject the null hypothesis that this term is equal to 0, and we conclude that there is an interaction effect between these two variables. The next method that you can use to calculate the interaction effect along with the standard error is as follows. So what I want to do is I'm going to introduce a new variable here, and I'm going to manipulate this equation to get the standard errors right in the equation. So I'm going to show you these calculations here. So this is what we are interested in knowing. Okay, so we are interested in this theta 1, and we see that this theta 1 is actually equal to beta 1 plus beta 6, 2.59, exactly what we are looking for, and it will contain the standard error of this term as well. So let's go ahead and create a new variable, and this variable will be this, prior GPA minus 2.59, which is the average prior GPA. So what I'm going to do, I'm going to calculate the mean prior GPA in the sample by using this command and subtract it from every observation, and then I'm going to attach it with the data and regress the model. Okay, so let me show you everything on one table. Okay, in the model 1 we are able to get 0.78 by manipulating this equation by inserting the mean value. However, we could not get the standard errors. As we can see in the second equation, theta 1, that is the coefficient value of attendance rate, it is giving us this value straightforwardly, and this is exactly what we are getting here, 0.008, which is rounded to, I'm sorry, this should be 0.0078. So we are getting 0.008 right here, and we are also getting the standard error, and the t-value is about 3, which means this interaction effect, it is statistically significant by using this equation. Also note that all the other coefficient values, they are identical across these two specifications, as we saw in one of the previous examples where we were manipulating this type of equations. The constant is identical, the impact of the interaction term and their standard errors, everything except the coefficient value and the standard error of a variable of interest, it is different. So this is the way of getting average partial effects, also called average marginal effect of interaction terms. And you can use it in the quadratic model, in the interaction model, and any other nonlinear models. Remember that the standard error associated with the interaction term, it's not showing you the statistical significance of the interaction term, because there are two coefficient values associated with this interaction term, beta 1 and beta 6, and you cannot calculate the standard error straightforwardly. You have to manipulate this equation to get the standard error, and as I showed you in this example, you can get these standard errors in this fashion. So be careful while interpreting these models with interaction term, that their coefficient value and the statistical significance, it is of little importance. Also, note that the coefficient value of attendance rate is negative here. We have to be careful in interpreting that attendance rate decreases the final outcome, because this impact depends on prior GPA, and this coefficient will be meaningful if prior GPA is 0, which means beta 6 is 0. Then beta 1 will represent the change in the standardized outcome on a final exam as a result of change in attendance rate. But since we have this variable prior GPA attached with it, this means that this individual variable and its statistical significance, it's meaningless. So what we are more interested here is the interaction impact, which you calculate by this or using this, and then you get standard errors to see if this impact is statistically significant or not. All right, I'll see you in the next video. Bye bye.